In the previous videos, we've learned about vortex sheets, which is a sheet of vorticity. And we've also learned about the definition of airfoil geometry, or how that's defined. And so now we're going to learn about something called thin airfoil theory. Thin airfoil theory is a method of using a vortex sheet to approximate the aerodynamics that we would get from this two-dimensional airfoil. And really what this is an approximation. This was developed in the early 1900s as a method for predicting the lift and pitching moment on an airfoil. And it's actually fairly accurate, surprisingly accurate, when you see what kinds of approximations go into it. But it turns out that it's rather accurate, especially for airfoils that are relatively thin. And from experimental data, it shows that this is pretty accurate for airfoils that are less than about 12% thickness. And 12% is a fairly decent, a normal thickness that we would see on an airframe. So anyway, it turns out that this theory is actually rather accurate for many applications. Okay, so let's walk through some of the approximations here. We're going to start off with just a drawing of the airfoil. So this is X and Y. And we're going to take let's draw our camber line. That's our camber line. So camber line, Y sub C is going to be a function of X. Okay, so we've got some function that defines our camber line of that airfoil. Now, normally, then we would add a thickness around that airfoil to create the actual two-dimensional airfoil. But we're going to instead, we're going to look at just using the camber line to develop the aerodynamics here. And what we're going to try to do is make that camber line a streamline of the flow. So here we've got some incoming velocity at some angle of attack alpha. And what we want to do is figure out how to make that camber line a streamline of the flow. And the way we do that with thin airfoil theory is we place a sheet of vorticity along that camber line. So this sheet of vorticity can vary in strength, and the strength of that will be a function of X. So we're going to call this gamma of X naught. So X naught will be our variable down here. We're going to integrate over X naught along the length of this airfoil, and we're going to go from the leading edge to the trailing edge, and that has a length of C. Okay, so first thing we can do here is make some definitions about angles and in this geometry. So one thing to note is that there, at each point, the camber line makes an angle with the x-axis, and we're going to call that phi. And at that point, we've got a normal velocity and a tangential velocity. Okay, so we're looking at this point of interest here. Okay, so let's write down a few things that that we can now understand from this this development of using this sheet of vorticity along the camber line. So the first thing would be that the tangent of phi at any location x is equal to the change in the camber line with respect to x. Okay, so we've got our camber line definition over here as a function of x, and the derivative of that with respect to x is the tangent of phi. Okay, so in other words, we can rewrite that as phi of x is equal to the arctangent of dyc dx. And I mean for all of these to be d's. Okay. So now let's write the velocity in the x direction at this point here, at the point of interest. Well, that velocity is the summation of the free stream velocity plus the velocity induced by the vortex sheet itself. And so that's equal to, so the velocity in the x direction would be v infinity cosine of alpha. That's the velocity in the x direction from the free stream. Plus, I'm going to call this the tangential velocity induced by the vortex sheet times the cosine of phi minus the normal velocity induced by that vortex sheet times the sine of phi. Okay, so that's the velocity in the x direction at that point of interest. And the velocity in the y direction would be v infinity times the sine of alpha plus the tangential velocity induced times the sine of phi plus the normal velocity induced times the cosine of phi. So what I should point out here is that the normal velocity and the tangential velocity that I've written up here, those are just the velocities induced by the vortex sheet. We add those together with the free stream now to get the velocity in the x direction and the velocity in the y direction. Okay, now one last thing is that in order for the camber line to be a streamline of the flow, that means that the change in camber line with respect to x, or that slope, has to be equal to the velocity in the y direction divided by the velocity in the x direction. That simply is stating that the velocity there at that point is tangential to the slope of that camber line, or is tangential to the camber line itself. Okay, so we can substitute now in the Vx and Vy into this equation here. So we're going to get V infinity sine alpha plus V tangent sine of phi plus V normal cosine of phi divided by V infinity cosine alpha plus V tangent cosine of phi minus Vn sine of phi. Okay, and one last thing is that we also have this relationship here. I'm going to bring down and say that the dyc dx can also be expressed as the tangent of phi, okay, at any location. Okay, so let's now rewrite this equation. Let's just rearrange it a little bit, and as I'm going to take this term on the bottom here and move it over to the left-hand side, and the first term, see, as I move it over to the left-hand side, because these two are equivalent, I can multiply the different terms within that, within those terms. I can either use tangent of phi or dyc dx to multiply each of those terms by. So the first one, I'm going to choose dyc dx times v infinity cosine alpha plus, now we've got a vt times cosine of phi on the bottom there that I'm moving over to the left-hand side, multiplied by the left-hand side, and this one I'm going to multiply by tangent of phi. And then the third term there is minus Vn sine of phi, and I'm going to also multiply that by the tangent of phi. Okay, so that's my left-hand side now, and that all is equal to the stuff on the right-hand side, which is V infinity sine alpha plus Vt sine of phi plus Vn cosine of phi. All right, and now there's one identity that we want to use here, one trigonometric identity, and that is that the cosine times the tangent is equal to the sine. So we can swap that term out, and now we see that we have this term on the left-hand side that's equal to this term on the right-hand side, and so we can cross those out. Those two will cancel. Okay, so let's just rearrange now from what we have, and I'm going to move the v infinity terms to the left-hand side and pull that outside. So we're going to have v infinity times dyc dx cosine alpha minus sine alpha. So I moved both of the v infinity terms to the left-hand side. And then I'm going to move the vn terms to the right-hand side. So that will be equal to vn times cosine phi plus, we've got a sine phi and a tangent phi up there, multiplied by vn. Okay, so up to this point, we've been pretty general about how we're handling angles and everything, but at this point, it's helpful to make some approximations that are going to simplify these equations. And the first approximation we're going to make is that phi is small. Okay, so we're basically saying that the slope, so the camber of most airfoils is on the order of somewhere around 2%. And remember that the maximum camber here is the maximum height there of that camber line relative to the x-axis. And most airfoils are on the order of 2% of the length. The camber is maybe 2 to 4%. And so phi is pretty small. The slope of that camber line is usually pretty small. So if we say that phi is small, then we can use a small phi approximation. That is that cosine of phi is very near to 1, and that sine of phi can be approximated by phi itself, and that the tangent of phi is also very close to phi. Okay, so now I can plug these in, and what I get on the left-hand side is still v infinity dyc dx cosine of alpha minus sine of alpha. And then on the right-hand side, I say that's equal to Vn, and instead of cosine of phi, I've got 1, and instead of sine phi and tangent phi, I've got phi squared. So this term here became a 1, this term became a phi squared, and because phi is small, phi squared is extremely small, especially compared to 1, and so we can actually drop that out so that on the left-hand side, all we're going to retain is Vn, because we've got Vn times 1 plus phi squared, which is very small. So we're going to drop out that second term, and so we're left with this equation here for how the normal velocity is related to the slope of the camber line and the free stream angle, or the free stream angle of attack and the free stream velocity. Okay, so at this point we need to walk back to our development of a vortex panel, and up here we're using a vortex sheet to represent this camber line, but when we said that phi is small, we can approximate this sheet by simply allowing that sheet to lie on the x-axis itself and still vary in strength, but we're going to assume that this sheet of vorticity here just lies on the x-axis itself, which makes it a vortex panel, actually. So from vortex panel, from the previous development that we've gone over before. The velocity in the y direction of a vortex panel is equal to minus 1 over 2 pi times the integral from x naught equals 0 to c along the chord length. And then it's x minus x naught times gamma of x naught, so the strength of that vorticity. And then x minus x naught squared plus y squared dx naught. Okay, so this is the velocity in the y direction at any point. We can plug any point in x or y relative to this vortex sheet that is lying on the x-axis, okay? And we can get the velocity in the y direction. Now, what we need is the normal velocity that is induced by this sheet. And so the normal velocity is the y direction if phi is small, right? So if that panel lies on the x-axis, then the normal velocity here is simply in the y direction. So we're going to say that Vn is about equal to Vy, or very, very nearly equal to Vy. And we're only interested in that velocity actually where y equals 0, or in other words, on the camber line itself, or the chord line, once that camber line has been smashed down to the chord line through the approximations that we're using here. So that means that this y is equal to 0 here. So we can simplify this and say that Vn now is equal to minus 1 over 2 pi the integral from x naught equals 0 to c. And because y here is 0, the x minus x naught terms will cancel, or at least one of those cancels, and we're left with gamma of x naught over x minus x naught dx naught. And now we can equate these two results for Vn and say that that 1 over 2 pi the integral from x naught equals 0 up to c of gamma of x naught over x minus x naught dx naught is equal to v infinity. Now I flipped the sign on Vn, so I'm going to flip the order of the things inside the parentheses here. So v infinity sine alpha minus dyc dx times the cosine of alpha. Okay, so this is the general solution for thin airfoil theory. This is the general equation, and basically what we input into this equation is a camber line. So we know the camber line slope at each location in x. We can get the derivative of that. And what we want to know is the distribution of gammas that then satisfy this equation. And so what this equation does is it actually limits the distribution of gammas that we can use, but if we choose the correct distribution of gammas, this will force the velocity here, or the camber line, to be a streamline of the flow. Okay, so now our job is to find the distribution of gammas that satisfy this equation here. Now there's two things I want to point out. The first is that in most developments of thin airfoil theory, they make one more approximation that I did not include here because it's not necessary to solve this problem. But one more approximation that they usually make is that the angle of attack is also small. So if alpha is small, then sine alpha can be approximated as alpha, and cosine of alpha is about 1. And so the right-hand side of this equation becomes v infinity times alpha minus dyc dx. Okay, so it's a little bit of a simplification, but it turns out you don't need to do that in order to get a solution for thin airfoil theory. But that is one common thing. In fact, I think you'll see it in basically in every aerodynamics textbook that they'll make that approximation as part of thin airfoil theory. So that is the more general or commonly used solution of thin airfoil theory is using this term on the right-hand side, but it's not necessary. Okay, the second thing I want to point out is that our next job is going to be to find these gamma distributions that satisfy this equation. But we have one piece of information that's going to help us, and that's called the Kutta condition. So the Kutta condition simply states that at the trailing edge of an airfoil, we want the velocity to come off of this airfoil so that the velocity is tangent to the direction of, or I guess the average of these of the angle here. So it would come off tangent to that angle there. And for that to be true, now we've learned that that over a vortex sheet, if we come back up here to our drawing of the vortex sheet, we've learned that at any point here, as you move across a sheet, you'll have a step change in the tangential velocity that is equivalent to the strength of that sheet. So we covered that in a previous video, that the step change here is equivalent to the strength of that vortex sheet. So if we want the tangent or the tangential velocities from the upper and the lower surface to be the same at the trailing edge, that means the strength of the sheet at that location has to be equal to 0. So what we know is that gamma at C, which is the chord length at the trailing edge, has to be equal to 0. And that is called the Kutta condition, and that will force the trailing edge then, or the flow, to come off of the trailing edge tangent to the trailing edge because there's zero vorticity strength there due to this vortex sheet.